There are just a couple of slides from the previous lecture, which I would like to show you. So are we in good shape? So this is Shimon Edelman's Riddle of Representation. Two humans, a monkey and a robot, are looking at a piece of cheese. And the question is, what is common to the representational processes in their visual system? And the answer is the cheese. It's the cheese in virtue of which we will be able to make ontologies and indeed information systems, if we build them properly, interoperable, because there is something which can serve as a benchmark to make them work together, namely the cheese. All right, now we move to lecture number 6. This lecture is in 2 parts. The first part is about something called the semantic web. The second part is about how we can make the semantic web realize some of its goals by using a top-level ontology, and what top-level ontology we should use. So another way of formulating the problem of ontology in the modern age goes like this. In the old village societies of bygone eras, people could know everything that there was to know because they could fit it all into a single brain. Because there wasn't very much to know. You had to know about your fields, your farms, your maize, and also about your relatives, your neighbors, so forth. But even that small amount of knowledge involved an amazing degree of highly complicated integration. So consider what you need to know in order to grasp something as simple as an act of promising. So first of all, you have experiences of speaking and of perceiving somebody else nod when you speak. Then you have intentions, both your own intentions and the intentions of the people that you're speaking to, which may sometimes involve various kinds of masking because they want you to think that you have certain intentions when in fact you have other intentions. And to work successfully as an individual in a society, you need to be able to detect some of those things very, very quickly and reliably. You need to have knowledge of the language that you're speaking, which is itself a very complicated affair. You need to have knowledge of actions and of your own tendencies to act. So when you make a promise, you commit yourself to acting. And to be committed to acting means not that you have merely some mental change of state, but also that mental change of state is accompanied by a tendency in your future for you to realize the content of that mental state. And then you have various kinds of deontic knowledge about obligations, that when you make a promise you become obliged, about the other person's claim upon you to realize the content of the promise. If the promise is made in some kind of context where you're dealing with somebody who is of a higher rank than you in the village social order, then you may have knowledge of the authority relations which you are engaging with, and so forth. And you have to have knowledge of a whole series of background phenomena, like the habits of the individuals involved, your own habits, your own mental competencies, other people's mental competencies, physical competencies, skills. All of these things are integrated together in your mind in order to make simple transactions possible. So I take a bushel of wheat from your farm and promise to give you 6 chickens tomorrow. That's a very simple transaction, but it involves very many, very complicated, fine-grained types of knowledge on the part of the people involved, if such transactions are going to work well across society, across generation. Now, of course, people are not aware that they have all of these kinds of knowledge. the knowledge is tacit. It's rooted in their in the way that they are as human beings in that kind of society. But it's there nonetheless. Complex knowledge, which is captured in human beings who work together in societies successfully, even in the simplest of societies. And the reason why I'm saying all of this is because one of the goals of the semantic web when it was initiated, and I'll describe some of that in a minute, was to create e-commerce. E-commerce means that you carry out those kinds of simple exchanges electronically on the web, where you can't look into the eyes of the person that you're negotiating with, where maybe there is no negotiation, there are just a few clicks, and that bang, you're home. Now, some of these e-commerce projects have been successful. Amazon.com, for instance, is wildly successful. But many of the e-commerce projects which were associated with the original dreams of the semantic web failed. The B2B ideas that were originally forward were very difficult to implement, and they were very difficult to implement in part because of all this background knowledge that is very, very difficult to capture and express, both in general terms when it comes to providing ontology-like theories of it, but also in specific terms when it comes to instantiating it within the spatio-temporal context, within specific people, when the people themselves come together only virtually. So the problem is, how could human beings effect the same sort of integration, whether in the social case or in the case of high-throughput bioengineering, or whether in other kinds of cases? This is a difficult problem. And the semantic web was outed as a new silver bullet which would solve this problem, integrating data in reliable ways to make all kinds of things much more efficient. So the semantic web was designed to be the next generation of the internet. It was designed not merely to allow content to be made accessible on the web, but also to be useful, because the content would be integratable on the fly to a large degree without human interference. And the way it was described initially was via dramatically better support at the level of metadata, which will yield the ability to query and integrate across different conceptual systems. This already makes me feel queasy. I think the only way in which you can query and integrate across manifold domains is if you pay very careful attention to understanding the reality which is being described through that data. And if you try and integrate conceptual systems, then that suggests to me that you want to ignore reality and work only with information or conceptual model type things. And we've seen what happens in the previous lecture, and that is the case. So Tim Berners-Lee, the inventor of the internet, described it thus: we are going to have a more powerful web where documents and data will be annotated with special codes. Computers will be able to search and analyze these things automatically, and so forth. And these special codes are going to be created in special code systems called ontology, which will be used by web authors. So the idea is that you will not just write your website using HTML. Your HTML will be created within the constraints of ontologies, which will be built into web creation systems in such a way that your ontology will be shared by someone else, and therefore the content that you create on your website will be shareable by the someone else, because you both share the same ontology. So these ontologies will be used by web authors to explicitly define their words and concepts as they post their stuff online. And these codes would let software agents analyze the web on our behalf and make smart inferences that go far beyond and so forth. And then there were various tools which would be exploited for this purpose. So XML, Extensible Markup Language, RDF, Resource Descriptor Framework. XML is really a cleverly expanded HTML type piece. RDF is a database resource brought into the semantic web world. And the important thing from our purposes is the ontology web language. We talked yesterday about first-order logic. OWL, but it's actually web ontology language, spelled OWL. It's a fragment of first-order logic which has nice computational properties, which we will talk about a little bit in a minute. And so you can find out about the web on this at the OWL on the web. There are different flavors of OWL which have different degrees of expressivity. So you can say more in the top flavor called OWL full than you can in the flavor which is usually used, which is OWL description logic. But OWL full, it doesn't have the nice reasoning properties of OWL DL. So most people choose OWL DL because they want to do reasoning. And they want to have assurance that reasoning will complete, that the computer program will actually terminate and give you a result. And with OWL DL, you have assurance that that will happen. The first problem is that you can write ontologies in OWL. There are tools like Protégé which enable you to create OWL ontologies for your own personal, private sphere, for instance. But the result is not necessarily any good. And it may not be an ontology in any sense which is recognized by any other human being on the planet. It may just be good OWL. But if you define an ontology as anything which is written in correct web ontology language, then you will end up having a meaning of ontology which includes what we can only call teenage nonsense. So let me find you quickly. Well, anyway, we'll come back to the teenage nonsense in a minute, but an example would be an ontology called kissology, which is an ontology of kissing, which consists of only one term, namely kiss. This is an ontology which is posted on the web. In fact, it was posted for a long time on the W3C website. W3C, the World Wide Web Consortium, which maintains the OWL standard. There is a lot of teenage nonsense on the web. There is also some teenage nonsense ontology on the web. Now, another example, which is not teenage nonsense, but which is nonetheless problematic, is this is taken at random. You can find thousands of web ontology. This is called the ubiquity publication ontology. And I'm not going to read this, but we have here a person and author. And this says, roughly speaking, that a person is an author. So the class of persons is a subclass of the class. Sorry, the class of authors is a subclass of the class of persons. So an author is a person. That's probably good enough. But now we have chapter is a subclass of string. Now, I'm not sure that I approve of that. A string is a string of characters in some determinate language like ASCII. I'm not sure that that is a good count of what a chapter is, particularly if you have a goal of producing a publication ontology which is going to be of general use. And I don't want to worry about this. I just want to give you some idea of the flavor. Another example, which is not actually an ontology created within the semantic web, but which is an example of the kind of thing which is created, is the enterprise ontology, which defines a sale as an agreement between two legal entities for the exchange of a product or a sale price. Now, I think agreement is probably wrong. You need more than an agreement of a sale. You actually need to execute the sale. And then a market is all sales and potential sales within a scope of interest. Again, that is not, it seems to me, going to provide a very precise and nuanced facility for reasoning about things like sales within markets. But this is the level of precision that you would find within the early days of the semantic web ontology development work. Now, remember, the assumption behind all of this work is that issues of communication and compatibility are going to be solved automatically by machine. And for this reason, ontologies have to have nice computational properties which enables them to reason quickly, because decisions are going to be made in real time about transactions on the web between large business organizations. And so computational tractability becomes a very important consideration, and this means that we have to make compromises when it comes to expressibility. The reason why the semantic web ontologies, particularly the early ones, tended to have rather superficial content is because they were subjected to very severe expressivity. Right? You can't say much, then you can't say much that is complicated and nuanced. So OWL-DL is regarded in many circles as the best you can do at the moment when it comes to finding a good compromise between the kind of expressivity which you get in the richer languages like first-order logic, but still have a decision procedure so that you can rely on the fact that a program will terminate. And this use of OWL-DL brings one great benefit when you're building ontologies. You can constantly test whether your ontology is consistent and get an answer immediately. This is true even if it's a very big ontology. Where in the bad old days, you would put an ontology together and you had no idea whether it was consistent. And there was really no way in which you could have an idea because the ontologies, the really big ones, were not surveyable by human beings. Now, OWL-DL is a good ontology primarily, I believe, for capturing static combinatorial information. For instance, information about pizza. So there are 16 different pizza toppings. You can have 3 of these and 2 of those, and that gives you a certain number of combinatorial possibilities with pizza. And the pizza ontology is a nice tool for representing those combinatorial possibilities. But when it comes to dealing with dynamic things, with change, when it comes to dealing with instances in reality which are highly complex, like organisms or human negotiations and so forth, then it's less good. All right. Now, some examples of the kinds of problems that you face if you have this combinatorial resource. We have SARS, which means severe acute respiratory syndrome. But of course, SARS is not severe acute respiratory. Not every severe acute respiratory syndrome is SARS. SARS is a specific severe acute respiratory syndrome, which was first identified 10 years ago, and which is associated with a specific coronavirus and with mutations of that virus which were identified in a certain laboratory in Melbourne in a certain year. So SARS is actually not just a combinatorial affair made up of severe acute and respiratory syndrome. It's more than that. And to capture that more is quite difficult, and it's almost a philosophical issue. Now, there is a gentleman called Clay Shirky, who is he is a very wise critic of the semantic web, and I'll just go through his criticism very quickly. So the logic of the semantic web is roughly the same logic as the logic which was already familiar to Aristotle. It's the logic of syllogism. It's a fragment of first-order logic. Can't do complex multi-type relation, just as the syllogism can't do complex multi. But it can do inferences like this really well. Humans are mortal, Greeks are human, therefore Greeks are mortal. Another example, which is somewhat more interesting. No interesting poems are unpopular among people of real taste. No modern poetry is free from affectation. All your poems are on the subject of soap bubbles. No affected poetry is popular among people of real taste. No ancient poetry is on the subject of soap bubbles, therefore all your poems are bad. That is a piece of syllogistic reasoning, which gives you an interesting conclusion. The semantic web, OWL-DL kind of ontologies can do that kind of reason. So Shirky then points out that the promise of the semantic web is that it will improve all the areas of your life where you currently use syllogism, which is probably very few, at least consciously. So most of the data we use in our everyday lives, including all the data we use when we judge whether somebody is a trustworthy partner for a commitment and deliver bushels of wheat, is not syllogistic. Moreover, it's partial and inconclusive and context sensitive in ways which you probably don't consciously appreciate. It involves a lot of guesswork and extrapolation, and none of that work can be done within an OWL-DL, or indeed with any kind of ontology approach, because it's not explicit. It's tacit. It's below the level of what you could bring to conscious representation in the normal case, unless you were an expert psychologist who was aware of the specific subject matter in hand. But then that information would not be useful to guide your behavior. So we almost never use syllogistic logic. But still, it's the case that there is a huge amount of heterogeneous data in the web and that we would like to query and integrate across it. It's unlikely that the semantic web is going to help us with everyday purposes of tentative negotiation. But it certainly is the case that we can use the web as a fantastic source of all kinds of interesting data. And to do that, the ontology idea can indeed be of great help. So the idea, the semantic web idea in its useful version, is to create terminological compatibility between different web pages created, for instance, by different research groups in different hospitals or in different universities, using common ontologies which satisfy the same logical constraints. You use those ontologies to annotate the content of the website, and all of that would be a great achievement. It would involve creating an ontology czar in the White House, or better still, in the United Nations, and telling everybody to use these and these ontologies when creating research content courses on the web. But the problem is that Tim Berners-Lee, who is the creator of this idea, was simultaneously a true believer in the virtues of all of the freedoms I exemplified by the existing web. The existing web is a fantastic pool of chaos. The semantic web is supposed to be a somehow coherently organized sub-pool which will enable the sharing and integration of data because of the use of good ontology. But anybody can create ontologies using OWL-DL, and not everybody creates good ontologies. And so long as the freedoms reign, they will create multiple ontologies. And so the integration possibilities which the semantic web represents will probably will be realized only with great difficulty. So let's see some of the difficulties which arise. So you have person name, and somebody else has name. So somebody builds an ontology in which the proper names of persons are called officially person names, and somebody else built an ontology in which the person names are just called names. And then you throw, I'm quoting now, you throw all of the information together and get a processor to think about it. And you can see that this probably will not work. So in one database, you have person name is John Smith, and in another database, the same person is listed under name equals John Q. Smith. Are they the same person? We know that. Could the data know that by being thrown together? Probably not. Now, there is now a huge industry of people who believe that you can take different web content created on the basis of different terminologies like this and map between them. Name, person name probably means the same thing. Let's map all of that data together. This is a non-trivial component of the American economy at the moment. And it, I believe, is to a large degree wasted investment. And it's investment which comes about because mappings between ontologies are having to be built retrospectively on the basis of guesswork of one or another kind, rather than creating good ontologies which everyone shares in the first place prospectively, and then the problem of mapping wouldn't arise. Now, this is an example from Werner. The XML is supposed to solve this problem for simple bodies of information. So let's try a business card. This is Jules Derry, whose business card, it has been represented in XML in order to make everything clear. And so we have first name. This is a business card. And then we have first name, Jules. That's made very clear by XML. But is Jules the first name of the person who has the business card, or is it the first name of the business card? Now, you know the answer to that question, but could a computer know the answer? Computers are stupid. And then we have that the XTC group is a member of, and we have Newco is a company. But what is the other term of the relation member of? Is it Jules, or is it Newco, which is a member of the XTC group? Again, the XML representation doesn't give you that in. And you can't extract that information computationally with any kind of confidence. And you certainly couldn't convert this into an OWL representation. OWL would allow you to capture that distinction explicitly, but that distinction has to be entered into the OWL. It was not entered into the XML. Will it be entered into the OWL only if the person who's building the OWL representation knows what they're doing? And evidence suggests that many people don't know what they're doing. So these are phone numbers, fax numbers, and so forth. Do they belong to Jules, or do they belong to the business? Again, the XML doesn't tell us. So the more Clay Shirky, the semantic web, with its neat ontologies and its syllogistic logic, is a nice vision. But like many visions that project future benefits but ignore present costs, it requires too much coordination and too much energy to be effective in the real world. A world of exhaustive, reliable metadata would be a utopia. As some of the problems that he lists, your meta-utopia is a world of reliable metadata. But some people deliberately will lie, because then their products will come higher in the semantic web's reasoning comparison engine. So we need coding police. And those coding police, in fact, I think we need coding police generally, but the problem is who will train the coding police and who will decide what regulations the coding police follow. Only if the coding police already have a good ontology of everything will they know how to police the coding. But then again, we're back at the beginning of our problem. But people are lazy. So many web pages are titled, "Please title this page." People are stupid. So just look at how many spelling mistakes there are on websites. And in order to tag using OWL-DL, you need not merely to spell correctly, you need to use the resources correctly. And that means not just using the resources in such a way that the error checkers, the automatic error checkers, can find syntactic errors in what you write, but they also would need to find content errors of the sort that we've been describing at various points in these lectures. And then the most important problem is that there are multiple descriptions because there are multiple ontologies. And we need to maintain the possibility of multiple descriptions where we're dealing with new kinds of information, where people need the freedom to formulate new ideas. But we don't want to enforce an ontology which will constrain people's expressivity in ways which would destroy what they're trying to do. For instance, discover how genes work. So we have a problem here. On the one hand, the semantic web vision will work only if people already speak in the same way. But on the other hand, we want the semantic web to help in difficult areas of research where we precisely do not want to constrain what people say because they want to say new things. And then there is another aspect of this multiple representations problem, which is called ontology impedance or semantic mismatch. So there are multiple ontologies, and however hard you try, many of them just can't be matched together, even when they're about the same domain. There are various solutions to this problem. One is to treat it as inevitable and learn to find ways of coping. And the other is to resolve the impedance by hand on a case-by-case basis. And both of these solutions fail. So first of all, if you have mismatch between ontologies and you say, okay, we'll just cope with it, 4% of the terms are mismatched. But then when the next layer of ontologies is created, those errors in that 4% of mismatch will propagate and it will become 16%. And so forth until, and in an area like medicine, we can't allow that kind of propagation. And the second problem won't work. Second solution won't work because the whole point is that that the semantic web is going to solve these problems automatically on the fly to save people time. But if everything has to be checked on a case-by-case basis by humans, then the time-saving benefits of the semantic web will be lost. Now, one popular solution, which is embraced by Clay Shirky and by many leading proponents of the semantic web today, is the idea of lite ontologies. The idea is that we shouldn't try hard to produce good ontologies of rich domains. Rather, we should allow lots and lots of little ontologies of tiny domains and then throw them all together, and somehow something wonderful will happen. And I think it will be clear by now that I'm not entirely enthusiastic about this approach. And the evidence is that it didn't work. So we had this for a time, and the semantic web produced this kind of thing. So this is the teenage stuff that I promised you. So in the early days of the semantic web, 2002-ish, there was a web page, an official page of the W3C organization called Schema Web Ontologies, which I always used to include in presentations about the semantic web because it's so silly. So it consisted of a long list of things like the music brain's metadata vocabulary, or the beer ontology, or the pet profile ontology. These were touted as being the achievements of the semantic web. And from the beer ontology, for instance, which was correctly constructed as an owl ontology, you could infer that every beer that ever exists, every portion of beer that ever existed or ever will exist in the universe was made from one single hop. Now, it was checked very carefully, otherwise it wouldn't be here, but it was checked from a syntactic point of view. And to do good ontology, you need to think. You need to think about what you're doing, and you need to think about the world that you're trying to represent. And these were built by teenagers. Literally. Now, that website, and this is a sort of piece of good news, it no longer exists. And maybe you can find it somewhere in some dark tunnel. But it's been taken off the W3C area of the web, it suggests that adults are gradually beginning, or maybe people are listening to me, I don't know. Maybe they're just afraid of being humiliated. So the problem with lite ontologies is that they usually don't generalize. They repeat work already done by others. You can't combine them together, even if you would want to. You can't see ways of improving them progressively. They're deliberately designed to be simple, They reproduce the silo problems. In fact, they make the silo problems worse. But they are the very problems which ontology is supposed to solve, at least as I conceive ontology. And then finally, they're often used in sloppy ways. I'll just give you one example. This is an example of the way in which the semantic web is being used to capture information. So we have Yo-Yo Ma, whose birthplace is Paris, France, which is located in France, and which has temperature 62 degrees. Now, there's something wrong with that. You're mixing here relatively permanent information. Yo-Yo Ma, birthplace, Paris is permanent, with something which is not permanent at all. And this is from the Handbook of Ontology, which is one of the textbooks of the semantic web. Retail price as a denomination instance of dollar. Now, I believe that there are retail prices also in Belgium, which are not denominated in dollars. But this says that retail price as such, as it were, has a denomination in dollars. And similarly, we have SI unit is instance of system of unit. Now, an SI unit is not an instance of a system. It's an instance of a unit within that system. Now, you can find these kinds of simple coding errors everywhere you look in the semantic web literature, even in the literature which is written by clever people. And that's because there is too little thinking, A, about the specific cases in hand, but B, about the needs of coordination. People thought about coordination when they were creating axioms like this, and they would realize that they need, first of all, to check how other people did it, whether they did it correctly, and how we can bring about a situation which we all do it in the same way. And that kind of attitude is gradually becoming more entrenched within the semantic web world, as we shall see in a minute, but which is very difficult to implement because the attitudes of Tim Berners-Lee, which are in favor of freedom and anarchy and creativity and all those nice things, mitigate against the coordination which is necessary to make good scientific ontology work in the way that good science works. Namely, everybody is working towards having a single unique representation of the relevant domain. All right, just another example. This is another textbook of semantic web engineering. A location is defined as a spatial point identified by a name. Now, this is a variant of the use-mention confusion. Not every location has a name. I believe that this room here has a name, but I doubt that this corridor has a name. Moreover, neither the room nor the corridor is a point. The definition of arrival place is given as a journey ends at a location. And the definition of a facet is a ternary relation that holds between a flame, a slot, and the facet. Now, these people need help. So we will be able to use ontologies in the way that the semantic web conceived only if they are ontologically coherent, and that means that they've been created on the basis of some genuine thought, and human beings can see that thought. They can recognize that this has been done correctly because it's been done intelligibly. They need to be logically coherent. Computational tractability is important, but they need to work well together, and as each part changes, the other parts should evolve in tandem so that we maintain consistency. And that means we need tested rules, which is the way we ended the previous lecture, tested rules or principles for building ontologies, which everyone shares, everyone agrees to. And this implies a new approach, which we call prospective standardization, which is the approach which is used in the realm of technical artifacts quite standardly. So standards for cell phones, for instance, or for internet servers have been built by engineers. They've been tested thoroughly over and over again. Once they've been tested, they are imposed as standards prospectively so that everybody has to work with those standards. What we need in the ontology world is a similar attitude of prospective standardization on the basis of testing, which means we need to have objective measures so we know what works, what passes the test. And this is a bit like traffic law. And it's a bit like science. So scientific theories must be common resources. You can't buy or sell a scientific theory. They must be intelligible to human beings. They must be open. They must constantly evolve to reflect new results. And then they must evolve in synchrony with the neighboring sciences. And they must be synchronized in such a way that the data coming from all of the people who are doing the relevant science is comparable in virtue of the fact that they use common systems of units, they use common mathematical theories, and so forth. So we want the web to be, the semantic web, to be subject to this kind of ethos rather than to the freedom and anarchy of a million blooming flowers, which some semantic web protagonists still defend. So the good news, as I say, is that the lite ontology movement seems to be losing some of its theme. So the schema web, music beans, owl ontology, as far as I can see, is no longer to be easily found anyway. There is some recognition on the part of the leaders of the semantic web for the need for greater coordination. This is only the beginnings, but these are good beginnings. Now, one example is illustrated here. So at the moment, the OWL-DL language constrains the use of the ISA relation. ISA means subtype or subclass. But other relations like part of are not constrained. You can define them as you want. Now, ontologies require more relations than just subtype, as we saw. There was a document which again has been removed from the web and corrected, where a suggested design model, a good practice for the use of part of, was composed. And towards the end of this document, there was the sentence, and then choose a name for this relation. So in other words, you had effort invested to find a good common way of representing the relation part of, but then that effort was wasted because the author didn't realize that everyone should call it the same thing. Otherwise, the whole point of having a common representation was lost. What we need is more coordination along those lines. And the W3C is in a position to create such coordination, but I believe that the coordination will come as a result of the fact that people like me are going to be testing ways of producing this extra coordination outside the official realm of the W3C, and then proposing it at a later stage as a kind of artifact of choice for those scientists who want to be part of an endeavor to create a common coherent suite of ontologies for doing their work. Now, in order to do this, in order to create a, we need a top-level ontology. We need an ontology of relations like part of, instance of, depends on, adheres in, and so forth. And we need a common set of top-level categories like process, continuant, dependent continuant, and so forth. And then the question arises, which upper-level ontology should we use? Now, an upper-level ontology should be a system of categories, and it should have the formal theory with definitions and theorems. And the idea is that the top level should be shared by everybody, and then each particular research group should take that top level and create its ontologies by populating downwards, by creating more specific representation of more specific universal. So the methodology is population downwards from a shared common core. And this common core should be of sufficient richness that we can resolve certain kinds of incompatibilities which standardly arise when people start building ontology. And we can resolve these things not by brute force, but by an intelligibly coherent strategy which people can embrace because they see that it is intelligent hearing. And now we need to choose a formal framework in which to do this work. And then we also need to choose a category system to do this work. Now, this is very briefly on the formal framework. There are 3 formal frameworks which people recommend, which can be reasonably recommended, I believe, from different points of view. First is the OBO format. And you'll find the information about this at a website called oboedit.org. The OBO format is the simplest of all of these formats, the most easily readable. If you see your ontology just in a flat file, you can read through the ontology. And the output of OBO can be just a flat file, but you can also output the OBO ontologies as trees that you can visualize. So you can edit the trees. The OBO editing tool is a very simple editing tool, which is used primarily by biologists, but it's used by many biologists, and it's well tested. It's something which has been around for some years, and it has nice properties for human users. Second is OWL-DL, which we've talked about. This is a W3C standard maintained by very clever people who are trying to push it to the limits of expressivity without sacrificing the nice computational properties. There are many tools. The most important, most used tool is the Protégé tool, which you can download for free. And Protégé is a tool for building our ontology. And again, you can have visualizations, but the standard visualization here is a hierarchy tree. A third alternative formal framework is called Common Logic. Common Logic is an ISO standard. It's a somewhat enriched, standardized version of first-order logic, which means that OWL-DL is a fragment of Common Logic, in effect. Common Logic is not computationally tractable, so a Common Logic ontology would not be decidable. Although, in other words, it could be that you ask it a question, even a very simple question, and you would never get an answer. But Common Logic has very nice expressivity properties, which means that if you want to express an ontology with adequacy to your content, if your content is complex, which most content is, then you will do better to start with Common Logic and then work out how to create a simplified version in OWL at a later stage. And so there are, within the biological world, and there is a link here from the Berkeley Biomedical Ontology Project, to experiments designed to show how Common Logic can be used to support the gene ontology. OWL-DL and OBO formats are, to a degree, interoperable. That is to say, if you build your ontology in the OBO format, then there are now converters which will create an OWL-DL version. And if you build your ontology using OWL-DL, and provided you don't use some of the OWL-DL specific tricks, you will be able to convert it back automatically to an OBO format. So to that degree, if you want to start with OBO, and that you won't get into any serious problems should you want to gravitate to OWL at a later stage. I think that's probably a good point break for questions, because this tool support is an issue which people find important. So are there any questions? Anybody? All right, so let's continue. So the science is not in the business of freedom. So scientists should not be free to do everything that they want to do. In particular, they should not be free to take existing terms and give them new meanings. It may be that they can do that if they are careful and open and provide a good definition, they can't do it just on a whim and not tell anybody. Similarly, the ontology part of science involves certain restrictions on people's freedom. The idea is that once we have an established area of science with journal publications, textbooks, and so forth, then we need to have terminological resources which are relatively difficult to change. And it needs to be such that people are trained in some people are trained in how to use those terminological resources in order to produce annotations of those very same journal articles so that the scientific information becomes accessible to a wider audience. Now, the question then is, how shall we constrain people's freedom in a nice way? So what should be the upper level ontology that we encourage scientists, and I believe others, to use? And there are de facto 4 options here. By de facto, I mean de facto as far as the public domain is concerned. There may be really fantastic proprietary upper level ontologies which are doing wonderful work for the Dow Jones business information world, or for the MI5 or something. I don't know. But as far as public domain, easily accessible, upper level ontology resources are concerned, we have 4 options. And actually, we only have 1 option, I will argue. But we'll go through the other options. So Psych is the oldest of these efforts. It was not named an ontology until quite recently. Originally, it was designed as an encyclopedia of human common sense, and Psych. Human common sense is going to include a lot of information which is not ontological. So it will include information like Albany is the capital of New York, or Bill Clinton was president of the United States between such and such and such and such. This is common sense information. But some of the Psych knowledge base contains also ontological information, which was entered by hand, but mainly by ex-philosophy students, actually, using first-order logic and creating, I don't know how many there are, but at least 1 million axioms. And the idea originally of the inventor of Psych, a brilliant artificial intelligence engineer called Doug Lenert, was that once we had the sufficient number of axioms, then the Psych would begin to think. Something like that. It was a dream of artificial intelligence in a former century. And there has been a lot of money invested in Psych over the years, a lot of customers, and the result is what you can recognize now, what is described by Psych as a large and broad ontology or knowledge base and inference engine. And an ontology here means a representation of knowledge. Now, the problem with that, so that philosophers, and I know this because I used to be one, sometimes get very upset by the way computer people use the word knowledge. Because for a philosopher, knowledge implies truth. If A knows P, then P is true. Knowledge is true, justified belief. Now, all truths are consistent. But the way computer scientists use knowledge, you can have inconsistent knowledge. Knowledge means scientific content, or it means information content. The Army has someone whose official title is Head of Knowledge, which means he keeps all the database. So from the Doug Lenert Psych point of view, knowledge, particularly human common sense knowledge, is assumed to allow contradictory information. So some people commonsensically have knowledge to the effect that you can turn wine into blood in a building. I assume you can infer that from the Psych knowledge base. Other people think that that's false. They both have knowledge, but they're different groups of people. And in order to do justice to this contradictory knowledge, information, or actually not really even very good information if it's contradictory. Psych uses microtheories, and each microtheory is consistent. The fact you have different mutually contradictory microtheories screens against the unfortunate consequences of having contradictory axioms in your system. Now, of course, one problem with this microtheory approach is that this ontology then no longer serves to counteract the silo problem, because the microtheories will lead to silo effect. But we'll come back to that in a minute. So there are other problems with psych. Psych contains many, many classifications. For example, it contains a classification of human type by cup size, where cup size A is defined as an instance of human type by cup size, which is an instance of partially tangible type by non-numeric size, which is a subtype of Homo sapiens, which is disjoint with cup size B, which is the collection of people with female breast cup size A, which is a human type by cup size is an instance of collection with an event-like order. Now, this is what is technically known as nonsense on stilts. So, psych has a type called collection of collections, and I think this may be what this is. The human type by cup size is an instance of collection with an event-like order. This is a definition. A collection of collections. Each instance of collection with an event-like order is a collection whose instances are conventionally regarded as being ordered by some relation Rho, where Rho orders the members of Col in the manner in which events are ordered in linear time. For example, the instances of distance are conventionally regarded as being ordered by the relation greater than. This ordering is event-like, so distance is a collection with an event-like order. So this collection with an event-like order is defined as this. Now, this is unhelpful to a human being. Anyway, to me, it's said to be helpful to people who purchase the site services. I'll just go through it. Biology microtheory is an instance of general microtheory. General microtheory is an instance of microtheory type. Microtheory type is an instance of second-order collection. Second-order collection is an instance of collection type type. Collection type is an instance of collection type. Collection type is an instance of collection type by disjointness. Collection type by disjointness is an instance of collection type. Collection type is subsumed by collection type. Collection type is subsumed by collection. Collection is an instance of collection. Plant is an instance of biological kingdom. Plant is a subset of vegetable matter. Plant is the collection of all individual plants. Cell is an instance of clarifying collection type. You believe that? Cell is an instance of biology topic. Flower, botanical part, is the collection of all reproductive organisms of angiosperm plants, may or may not look like conventional flowers. Now, a lot of people were building this thing, and the vision of Doug Leonard was that if you have a lot of people adding axioms, order will be created spontaneously. HL7 has a similar attitude, actually. HL7 has a lot of people creating various parts of this big e-health infrastructure independently, and then they vote as to which proposals should be accepted. But the people who vote don't always have sufficient knowledge of the reasons for specific choices by all of the different dispersed people involved. I believe that this kind of dispersed, distributed creation of large artifacts leads to problematic outcomes. And I rest my case.